Calculus. Differentiation from first principles. Example 1. Find the derivative of fx equals k from first principles, where k is a constant. Here's a graph of y is equal to fx equals k, where k has a value of 3. So every point along this line, the y value is 3. 0, 3, 1, 3, 2, 3, minus 2, 3, etc. So there are many lines fx equals k parallel to the x-axis. All points are on the red line here of interest. So y is equal to fx equals k. So our point xy satisfies this function. So if we put in the value of x, we find that the y value is on the line y equals k. If we take a different value, x plus delta x, a different value of x, we get f of x plus delta x is y plus delta y. And that too is equal to k. So another point, x plus delta x, y plus delta y, is also on this line. So we can find that even though the x has changed, the y plus delta y, is really the same value, k. Taking one from the other, y plus delta y minus y, is this line here, which is k, minus the first line here, k. K minus k. So we can cancel the terms out now. Y minus y, they'll cancel. K and k, they'll cancel. K and the minus k, leaving delta y is 0. So the change in y value from here to here is no change at all. It's still stuck on 3. So if delta y is 0, delta y divided by delta x is 0. 0 divided by delta x is 0. And at the limit, no matter how small our step is from x to x plus delta x, if it's only this amount or this tiny amount, we'll find that at the limit, delta y over delta x, dy dx is 0. So, we have now, for any constant, y is equal to fx equals k, that if we take the derivative of a constant, whether it's y is 3, y is 7, y is minus 2, dy dx of a constant is 0. The slope of this red line here is 0, and the function does not turn. It never increases nor decreases, it never turns. And it wouldn't matter what values we took, whether we took the values there, original values for x and x plus delta x, or any 2 points along that graph, we would find that the derivative of a constant is going to be 0. We don't always get the opportunity or have the requirement to draw the graph, so we might just do it using the formula. Find the derivative of fx equals k from first principles. So we write the function out, y is equal to fx equals k. The next step is to write y plus delta y, a small change in y, and that leads to a small change in x, fx plus delta x. And in this case, that's also equal to k, because regardless of what value we have in here, we're always going to get k. It doesn't depend on x. Y plus delta y minus y, subtracting the first line from the second, we get k minus k. Cancelling, we get delta y is 0, and dividing it by delta x, we get delta y over delta x is 0 over delta x is 0. And at the limit, when this gets very small and delta y gets very small, at the limit delta y over delta x is called dy dx, and that is equal to 0. Example 2. We now look at a linear function where fx is equal to ax. Find the derivative of fx equals ax. For example, fx is 3x, or what fx is 7x. And we're going to do this from first principles. So y is equal to ax. The next line is to put y plus delta y. And everywhere we had our x, we now plus x plus delta x. So instead of ax, we get a into x plus delta x. And multiplying in, we get y plus delta y is ax plus a delta x. Subtracting the first line from this line here, we get y plus delta y minus y is ax plus a delta x. minus ax. Now we can do some cancellations. The y's cancel and the terms in ax cancel. So delta y is a times delta x. But we want delta y divided by delta x, so we can divide both sides by delta x. So delta y over delta x is a times delta x over delta x. Or if we just took that across, we just find that it's equal to a. So we can see those terms cancel, or we find that delta y over delta x is a. And at the limit, when these are small, delta y over delta x becomes dy dx. And again, that's left equal to a. So if you differentiate y is equal to ax, you're left with just the coefficient that's there before the x value. So here's a graph of y is equal to ax. The point xy and the point x plus delta xy plus delta y slightly moved on from there. Change in the x value of delta x, a change in here of delta y. And we're interested in delta y over delta x, this ratio here, or the slope of this line. So for y is equal to fx equals ax, we found that dy dx was a. So the slope of that line was a. We just used the coefficient of the x. The slope is constant, it never changes, and the function doesn't turn. So this line continues indefinitely at that slope value and never turns, whether we used this point or a different point. So here we are, whether we used xy or this point down here, any point along that line, we would find that it has the same slope and the function does not turn. Example 3. Quadratic functions. Fx equals ax squared. Find the derivative of fx equals ax squared from first principles. For example, y might be 3x squared or 10x squared. How do you find the derivative from first principles? Well, we use the same approach as before. Instead of y, we substitute it with y plus delta y. And in place of x, we put in x plus delta x. So y plus delta y is a into bracket x plus delta x to be squared. Squaring x plus delta x, we get x plus delta x times x plus delta x. Multiplying across, we get x by x is x squared, x by delta x is x delta x by delta x is x delta x, and delta x by delta x is delta x squared. So bringing these terms together of x delta x and x delta x, we get x squared plus 2x delta x plus delta x to be squared, multiplied by a equals y plus delta y. So multiplying in now, we get y plus delta y is ax squared plus 2ax delta x plus a delta x to be squared. So that's our y plus delta y, and we want to subtract y from that. So y plus delta y minus y, this equation minus the first equation, we get ax squared plus 2ax delta x plus a delta x squared minus the ax squared. So now we can eliminate some of the terms. The y and the minus y, the ax squared and the minus ax squared, leaving us with delta y is 2ax delta x plus a delta x squared. We're interested in delta y over delta x, so delta y over delta x is 2ax delta x over delta x plus a delta x squared over delta x. So we can rewrite that expression now and again perform eliminations. The dx delta x cancels with the delta x, and the delta x squared divided by delta x becomes delta x. So delta y over delta x is 2ax plus a delta x. And as delta x gets very small, the limit of that, as it goes towards 0, delta y over delta x is called dy dx. And this being so small becomes 0 in effect when multiplied by a. It's still virtually 0, so we say the limit is dy dx is 2ax. So if we now look at the graph of y equals ax squared, we can see here's the quadratic form of it. Here's our xy, and our x plus delta x, y plus delta y. And we can find the ratio now of this delta y over delta x. And from first principles, we know that if y is equal to fx is ax squared, dy dx is 2ax. So the slope is 2ax. In this case, the slope is changing because depending on the x value, you get a different answer for the slope. We also see that this particular slope turns once. It's a quadratic, it will turn once. There's an example of a different value of the slope as we move from one point to another. There's our original and moving to another. And we can see that as we change our xy from here to here, the slope changes as we move. So the slope is changing and the function here will turn it as one minimum point or one turning point. Example 4. Cubic functions where fx is ax cubed. Find the derivative of fx equals ax cubed from first principles. So we start as before, we let y equals ax cubed. And we substitute y plus delta y for y and x plus delta x for x. So y plus delta y becomes a into x plus delta x cubed because it was ax cubed. X plus delta x to be cubed is x plus delta x times x plus delta x times x plus delta x. And expanding the first two out, we get x squared plus 2x delta x plus delta x squared from the cross multiplication of everything there. We now must multiply that by x plus delta x. So taking each term in turn, x squared by x is x cubed, x squared by delta x is x squared delta x. 2x delta x by x is 2x squared delta x, and 2x delta x by delta x is 2x delta x squared. Delta x squared by x is x times delta x squared, and delta x squared by delta x is delta x cubed. So a long expression, but there are some common terms there. There's an x squared delta x and a 2x squared delta x, which gives us a 3x squared delta x, and 2x delta x squared plus x delta x squared is 3x delta x squared. So the expression now is y plus delta y is a into all of that. But we can multiply a into it. So inside the brackets we get y plus delta y is ax cubed plus 3ax squared delta x. A by the 3x gives us 3ax delta x squared, and a by the delta x cubed gives us a delta x cubed. So we're interested now in the delta y, so to do that we take the original equation y plus delta y and we subtract the y from it. So y plus delta y minus y is all of that expression there minus ax cubed coming from here. So now we eliminate terms. The y and the minus y can eliminate each other. The ax cubed and the minus ax cubed cancel each other out. So we're left with delta y is 3ax squared delta x plus 3ax delta x squared plus a delta x cubed. So taking that to the next page, we have it written here, and we can now progress to look for delta y over delta x. So dividing now the top, both sides by delta x, we get 3ax squared delta x plus 3ax delta x squared plus a delta x cubed all over delta x. We can split this into three parts. We can say that's the same as 3ax squared delta x over delta x plus this part here, 3ax delta x squared over delta x, and then a delta x cubed over delta x. And now doing some elimination, those two delta x's cancel. Delta x goes into delta x squared just once, and delta x goes into delta x cubed, delta x squared times. So we're left now with delta y over delta x is 3ax squared plus 3ax delta x plus a delta x squared. And as we go for the limit, if delta x is tiny, really multiplying by a tiny number means that it disappears, and multiplying twice by a tiny number will mean that that term is really so close to zero it needn't be worried about. So at the limit we get delta y over delta x is dy dx, just this part here, 3ax squared. So if we look at the general cubic graph, a general cubic graph would have the expression ax cubed plus bx squared plus cx plus d. We can see that a cubic graph starts at one end and finishes on the other and turns twice. This one here comes to a maximum, then a minimum, and then keeps going. So we have these 2 points, xy and x plus delta x, y plus delta y. So for our function, where y was fx was ax cubed, we got that dy dx was 3ax squared. So the slope dy dx was 3ax squared. It depended on x. So in this case, the slope is changing. So as we move from one point to another, the slope here might change as we move down. So we can see that as we take different values for xy, this one as opposed to this one, we get a very different slope in the blue line. And if we move over here, quite a different slope again. It's turned to a negative slope. So for this cubic, the slope is changing and the function turns twice. It turns coming up here, it turns down from a maximum to a minimum and turns again. Example 5, polynomials. Differentiate 7x squared plus 4x plus 7 with respect to x from first principles. Here we've got a combined term with some term that's squared, a linear term, and a constant. So we're going to differentiate that with respect to x from first principles. So y is equal to 7x squared plus 4x plus 7. And everywhere we had y, we're going to put in y plus delta y. And similarly, everywhere we had x, we're going to put in x plus delta x. So y plus delta y becomes 7 times x plus delta x to be squared for the x squared, plus 4 times, instead of x, we get x plus delta x plus 7. So y plus delta y is 7 into x plus delta x by x plus delta x, plus 4 times x plus delta x plus 7. So y plus delta y, if we multiply those two terms together, we get x by x is x squared, x by delta x is x delta x, x by delta x is x delta x. They add to give us 2x delta x, and delta x by delta x gives us delta x squared. So 7 into that, plus 4 into x plus delta x is 4x plus 4 delta x plus 7. So if we take y plus delta y minus y and we subtract from this value here for y, we get 7x squared plus 7 by 2, that's 14x delta x, plus 7 by delta x squared, plus 4x plus 4 delta x plus 7, minus all of this term, that was the y, minus 7x squared, minus by plus is minus 4x, minus by plus is minus. So all of that is our expression in y plus delta y minus y. We can do some eliminations. The two y's on the left hand side will cancel. The 7x squared and the minus 7x squared cancel on the right. The 4x and the minus 4x cancel on the right. And the 7 and the minus 7 cancel. So we're left with delta y is 14x delta x plus 7 delta x squared plus 4 delta x. So we'll rewrite that now, and we're interested in delta y over delta x. So delta y over delta x, taking the first term, is 14x delta x over delta x. The second term is 7 delta x squared, taking it down, dividing by delta x, and then 4 delta x over delta x. So if we divide in now, we can see through elimination that those two delta x's will cancel each other out. That delta x into delta x squared will eliminate the square and just leave the delta x. And the delta x over delta x will cancel each other out. So we're left with delta y over delta x is just 14x plus 7 times delta x plus 4. And as we go for the limit, if delta x is tiny, infinitesimally small, well then multiplying it by 7 is still going to keep it very small. So at the limit, when delta x goes to 0, we can really consider these to be of 0 value. So we get delta y over delta x is dy dx, which is 14 plus the 4, but we ignore this term here because it's so small. So 14 plus 4. And if we were to do this without using first principles, we would say if y was equal to fx is 7x squared plus 4x plus 7. We were asked to do dy dx using the general rule, or f dash x. We would say leave the 7, take down the 2 as a multiplier, so 2 times 7 would give us 14, and reduce the 2 by 1 at the top, so it will be 14x to the 1, or 14x. In the case of differentiating 4x, we just call it 4, because we know that the coefficient before the x is the only thing that stays, and differentiating a constant we get 0. So 14 plus x is dy dx of this function, as we got through first principles also.